Okay, welcome everybody. So it's a wonderful day to have our members colloquium. Our speaker is Orit Raz, and she will talk about the Erd H unit distance problem and graph rigidity. Right?
Yes, thank you very much. Yes, indeed. So I'm going to talk about work in progress, joined with Joseph Szemer and Janusz Pach, where we so this work is related to a famous problem of Erd H called the Erd H unit distance problem. So we don't solve it, but we managed to do some reduction and to relate it to a different problem, a problem in graph rigidity theorem. So I want to explain to you about this today. So let me start by introducing the problem of Erd H. So Erd H distance problem. So what is this problem? So we're given a finite point set in the plane, P set, say n points, and we consider the set of pairs, or the pairs PQ of elements of P, such that the distance between P and Q is 1. And let's denote the size of this set as U of P. And the question is, how large can you be? Problem. In terms of n. Let's look at some example. Suppose that n equals 4. So we're looking at point set of size 4. For example, this one. So in this example, we have these pairs all have distance 1, and the other pairs no. So U of this set is 4. We have 4 pairs of distance 1. Can we do better for point sets of size 4? So yes, we can make these two vertices closer. Have this kind of point set. So of course the point set is only the vertices, but the edges show us where the pairs of distance 1. So here we have 5 pairs having distance 1. Can we do better? So no, once we fix the edge length here, the last one is determined, it's not 1, so this is the maximum. So I want to ask this in general. To define U of n, the maximum over all point sets, sets n of U of t. Okay, and it's clear. So in 1946, Erd H showed, if you look at this specific point set at the square root n by square root n grid, so this denotes the set of integers 1 to n, or square root n. Or the integer between 1 and square root of n. So if you look at this specific set and you look how many, so you need to scale it to make the repeated distance to be exactly 1, but essentially the number of unit distances here, the number of pairs that having the same distance is n to the power 1 plus c over log log. Yes, for some positive c.
So you're scale, so you're not looking for distance 1, you're looking for distance.
So you need to scale it to make the repeated distance be 1.
I can't see
You
the
can-
exponent. You can't see the exponent. I mean, like
It's
half
one
of the.
plus something.
It's what?
So where you have u of the square root of n cross the square root of n, and that equals, and then basically they can't see anything to the right of the equal sign.
Oh,
I can see n to the
That-
1
that's-
plus. It's-
Right, I mean, there's,
We're very
because the
curious
column-
what plus.
the column is,
so that's okay because it's more or less n, and this is the conjecture. It's smaller than n to 1 plus epsilon. But it says 1 plus c over log log n. Let's write it here. Okay. Wait. good thing that you tell me. So let's see. So Erd H, so 1946. Erd H showed that if this is our point set, square root n by square root n, integer grid, then the number of repeated distances here is more or less n to the power of 1 plus c over log n for some positive c. And Erd H conjectured that this is best possible. So conjectured is best possible. And since 1946, no one managed to find a better example with more pairs having the same distance. And people try to prove that this is the best possible, proving upper bound. Okay, so what do we know about the upper bound? In the same paper from 1946, Erd H showed that u n cannot be more than n to the power of 3. There was some more works here. We use my notes. And then in 1984, Spencer, Szemer, and Trotter showed that u of n is at most constant times n to the power 4/3. Then in 1990, Clarkson et al. They suggested to use a partition technique of the plane to tackle this problem, but their technique gave same bound n to the power 4/3. Then in 1995, Path and Agarwal suggested to look at epsilon s to tackle this problem, but the technique gave n to the power 4/3. Then in 1997, Seke introduced some new idea on using the crossing lemma to tackle incidence problem, and his technique applied to this problem yields same bound n to the power 4/3. Then in 2005, Pach and Tardosh, they had a new idea how to tackle this problem using forbidden subgraphs, and the technique gave un at most n to the power 4/3. Yes, this one faster. And even recently, in 2024, in the work of Tidor and Yu, they developed some sophisticated multi-level polynomial partitioning technique, but even in their paper, they say that when they apply to the unit distance problem, it gives same bound of un. Un is at most n to the power 4. Okay? So how come all these different results and ideas give the same bound of n to the power 4? So this is not that mysterious. There is a reason. And to see this, I want to give an equivalent formulation of this unit distance problem. Equivalent. Here's the other formulation of the problem. I'm not doing the mistake of putting my notes here again. Was it? So what is the equivalent formulation? So we're given, so now a new problem, we're given a set P of n points in R2. And we're given a set of n unit circles in R2. And we consider the set of incidences, I see, of all pairs point from P in a circle from C, such that this point lies on the circle. These are the incidences. The problem is upper bound. The size, the number of incidences. It's a problem, and it's an easy fact. See that this is equivalent to the unit distance problem, so U of n is up to a constant the same as the maximum of IPC. And we're all sets of size and points and n circles and unit circles. Well, it's the same, just we need just to use the simple fact that if we have a point, 2 points P and Q, and they have distance 1, then the point P lies on the unit circle centered at Q. So if we have a point set with many unit distances, many pairs that have the distance 1, we just take this point set and all the circles centers at points from this set, and we get P and C with many incidences, and also the other direction is correct. So if we have n points and n unit circles and many incidences, we can just take this point set, union with the centers of these circles, we'll have 2 n points and many unit distances. This is why they're constant. But up to this constant, these problems are equivalent. And if you look at this question, you can ask, okay, this is an incidence problem between points and unit circles. What about other curves in the plane? That's the same thing. And indeed, people looked at this problem, and the most basic instance of this problem is about bounding the number of incidences between points and lines. And this is a theorem of Szemer and Trotter theorem. From 1983. So it says that if we have n points in R2, and L is a set of n lines in R2, so instead of unit circles, we have lines, and we look at the number of incidences between the points and the lines, and this is bounded by at most n to the power 4/3, and importantly, this bound is tight. So for the point line incidence problem in the plane, this n to the power 4/3 cannot be improved. So the issue with all of these techniques is that they apply also to the point line incidence problem. So if they apply also to the point line incidence problem, we will not be able to improve the n to the power 4/3, except for Partardosh one that does not apply to this to point line incidence problem, but does apply to another incidence problem where the n to the power 4/3 this side. So in some sense, the reason that this unit distance problem is so hard is because if we have a new idea how to tackle it, we need this idea to be very specific to circles, to this problem. And so we need somehow to use specific properties of the unit circles. And maybe to add 2 more things to the so it's not exactly about the upper bound, but in 2010, there was a work of Erd H and Sharir, where they gave a reduction of another problem of Erd H called the distinct distance problem that is somewhat related. I'm not going to tell you what it is, but it was also considered very hard, and people worked on it, and they gave a reduction to reduction of distinct distances problem. To line incidence problem in R3. So this happened in May 2010, and then in November of the same year, Very quickly after that, Guth and Katz. So here they formulated some conjectures that if they are correct, will almost completely solve this, the Erd H distinct distances problem, the other problem of Erd H, and Guth and Katz managed to prove this conjecture. And so they almost completely, up to a square root of log n factor, solved this other problem, this Erd H distinct distances problem. So almost. So distinct distances problem. And to do this, they developed some new and powerful tools. In retrospect, they were very powerful. And people expected that after this progress, probably the unit distance problem is next. And people tried to use it, and so far, there was no success making progress in this other problem. So I'm trying to convince you that this question is difficult, and people try to improve the boundary, but they fail. Okay, so I want to tell you about our idea how to reduce this unit distance problem to another question in graph rigidity theory. But for this, I want to first of all tell you what I mean by graph, to give some introduction to this topic. So graph rigidity. Okay, so what do I mean by graph rigidity? So what is a rigid graph? So we're given some abstract graph, let's say m vertices, some set of edges, and we're given also, so this is a graph, and now we're also given an embedding of this graph in RD. With endpoints in RD, one for each vertex. Now let's look at the picture first, and then I'll give a formal definition. So let's say that we're in the plane, and our graph is K3, the triangle, and this is the embedding that we're given. 1, 1, square root 2. So when do I say that this graph is rigid? So what I want to do is I want to find some connected. So I want to find another embedding in the neighborhood of the original one, something maybe here. Another embedding of the same graph that induce the same edge length. And ask, is it possible? So of course it is always possible. You can always take a shift of the original graph or to rotate it, and you just get a congruent copy of the original graph. But the question is, can you find another embedding with same edge length, but not congruent to the original one? So in this case, this is impossible. Whenever we get a triangle with edge length 1, 1 square root of 2, we know it is congruent to this one. So the triangle is rigid. But if we look at if our graph is D equals 2, and sit here, D equals 2, and G is C4, and we look at this embedding, then in this case, you can always find in any neighborhood this parallelogram. You just like flex and move the original embedding to get this parallelogram with same edge length 1, 1, 1, 1, and in this embedding, so same edge length but not congruent to the original one. So this is not rigid or flexible. Formal definition. So first of all, if we have a pair of a graph and an embedding, call this the framework. Definition. Say that GP is a rigid framework. if there is some neighborhood of P, there exists neighborhood V of the original embedding P, such that for any other embedding in this neighborhood, so an embedding that is close to the original one, that for every P prime, V, we have that if P and P prime induce the same edge length, then P and P prime are in fact congruent. If they have the same edge length, then they are actually the same. So all the pairs have the same length. Okay, so this is the definition. And you can ask, so it looks like, so any questions so far? Okay, so it looks like in these two examples that it wasn't very important the specific embedding that I gave you. So if my graph is K3 and I'm in the plane, so any triangle that I will take here will still be rigid. It's just like the theorem from high school about the edge. And right, so I don't need anything special. And also for the C4 example, cycle of rank 4, I can take any other embedding, more or less, and still get something that is flexible. So maybe this notion of rapidity, maybe it is independent of the specific embedding. Maybe it's a property of the graph. It's a combinatorial notion.
For the case of the quadrilateral, there are certain cases where it's.
Right. Yes. Yes, so there is, yeah, I'm going to say it in a second. Question is graph rigidity is this notion is independent of the specific embedding P prime or is a property of G. And the answer is that yes, I can look at the graph and tell you whether I'm going to get something that is a rigid framework or a flexible framework, but only if my embedding is a generic one. So yes, and for generic embeddings P prime. So if my embedding is generic, then the answer is always the same. You give me the graph. So either for all generic embedding, it is the framework that I will get will be rigid, or I will always get non-rigid framework. So let me just examples. So as was already said here, so for example, C4, D equals 2, which is the cycle of rank 4. So for generic embeddings, the framework that we will get will be not rigid. So GP, not rigid. For generic P, but still for given embedding, so for example, for this embedding, say 1, 1, 1, and the last edge is of length 3, this is rigid. This framework is rigid. And another example with this picture here. And
Now that this was exactly what I had in mind, but
now that I'm thinking more, it's not rigidity. I can always, oh, I'm stupid. Patience is always taking, yes, ignoring my question.
Okay.
They're complex.
Okay, if you change your mind. Okay, so this is one, and the other example is again in the plane, if P is K33. So for generic embeddings, we'll get, so GP is rigid. For generic P. But if this is P, if this is the embedding, with points lying on two orthogonal lines and the edges are all crossing here, then this embedding, so K33, this is flexible. I can write down the formula of how to move the vertices here to get a continuous motion. So it's not hard to find.
Is it the points or is it just the distances of each edge that matter? I mean, if you specify a graph with the edges, you specify distance for each edge, is it then you don't need generic anymore?
So if you specify the edge lengths, they need to come from some embedding. I mean, not only
Valid, some legal.
a valid.
aspects.
And then your question is, what is this generic? If they, so what is your question exactly?
Then doesn't it matter how you choose the point? Once you've chosen the eggplant.
So okay, so if you if you give me the edge lengths and they correspond to some
Yes.
framework that is generic, then all other embeddings that will have the same edge lengths will also, I think they'll give the same answer. I'm not sure. Let me try to give you after that. Yeah, I mean, okay, I have later. I don't want to spend time on this, but there is an answer. I'll tell you. Okay, but the way I think of it is that you start with the embedding. This tells you the edge length, and then you. Okay. So this is more or less what I wanted to say about rigidity, but so notice that in the classical graph rigidity theory, people usually looked at the generic notion. So they said, okay, for generic embeddings, the answer is always the same. So now it's a property of the graph G. Let's try to characterize which graphs are rigid and which graphs are not by some combinatorial properties. Let's count edges, find cycles, connectedness, and let's try to understand this notion. But in the context of this talk, we do care about specific embeddings because we're going to look at configurations that come from maximizing the number of units, distances, so they are highly non-generic. So in this talk, I'm going to look at the notion of framework rigidity as I defined it. So we care about, so we have a graph and we have an embedding and we really care about this pair.
Is there that thing you mentioned, is there a nice criterion, abstract criterion on the graph that makes?
So for dimension 1 is just connectedness. For dimension 2, yes, just like some counting, you can show later, but you look at minimally rigid graphs and you just need to count, look at subset and see that you don't have too many edges in those subset. Then you spend some constraints inside the subset. But for dimension 3 and higher, this is open. Dimension 3, there is some conjecture, maybe it's true or not. And for dimension 4 and higher, there's not even a conjecture how to. It's a combinatorial property, but we don't even know how to.
But if I give you a graph and I ask you, is this rigid in dimension 3, do you have some kind of polynomial algorithm to say?
So you need to, you have a matrix and you need to compute the rank of this matrix with the polynomial entries, with the n variables.
So the answer is no.
Yeah, this is this issue. And again, but this gives you the answer for the generic problem. But if you ask me about specific embedding, then I don't even know how to check. Okay. Now. Small n matrices. So now let's go back to Erd H distance problem and see how we think we can use rigidity to tackle it. So back to the unit distance problem. So let me remind you what the problem was. We had points at P. And it says as N, I want to upper bound the number of pairs having distance 1. Upper bound. Use P. So go. Start strategy, so general strategy. So let's assume that we have a point set with many unit distances. Assume that U of P is at least n to the power 4 over 3 over log n. And we want to reach a contradiction. We want this to lead to a contradiction. So how will we get a contradiction? Maybe we can find some subset P prime such that if you restrict to this subset, you have too many unit distances there. So such that number of unit distances in P prime is more than the known upper bound. So let's write it like this. We'll get more. We'll even get, sorry, not n, cardinal to P prime to the power 4 over 3. I can write here even 2 minus epsilon, some very large. This definitely will give me a contradiction and will improve the current upper bound by log n. Small improvement desired. So, okay, so this is a set P. We have n points here, and we have many pairs having distance 1. So it's denser than this, but let's use this picture. And the idea is maybe you can find some P prime that has inside P prime, we have many unit distances. Then now we knew how we want to get P prime. So we're going to interpret this problem as a point unit circle incidence problem, use partition techniques of the pen, and find some subset that is very structured and very constrained. So this is the idea we had in mind, but we also knew that our tools, the tools that we use, apply also to the point line incidence bound. So if we show that there are too many incidents, too many unit distances here, we'll also show that there are too many point line incidences using the same technique, improving the n to the 4 over 3 bound for the point line incidence problem, which is impossible because this bound is tight. So we know we will not be able to show that there are too many unit distances inside P prime. So the new idea here is we are going to show that there are many repeated distances inside P prime, but maybe there is another number, maybe 7, that repeats again and again inside P prime. So many times that it leads to a contradiction. So that's the basic idea, but the question is how? So how can we find, so if we only have, we're only given information about pairs of points that have distance 1 between them, how can we say something about pairs of points that have another distance, another number, distance 7 between them? How can we find this kind of information with what we are given? And the answer is that this is exactly what rigidity tells us, right? It says that if I have a graph and you tell me these edge lengths, this determine also the length of this pair, the missing. So this is what we are going to show. So we can find a set E prime and many pairs, these are the red edges, and there is a graph that is generically rigid and many embeddings of this graph here. All of these embeddings induce the same edge length. So all the white edges correspond to pairs of points that have distance 1 between them. So all of these embeddings have the same edge length. Okay. So this is the picture. Let me see. So structure theorem. . This is with Szemer and Young Schwach. Notes for this? They still exist. Okay, so let's see. And so it's just this picture. I'm just trying to write it down. So it's good. Here, so there is some subset P prime. This subset is going to be a cardinality more or less n to power 1 over 3 up to some log n factors. Uppercase n, and there is some generically rigid graph. H with two vertices, at least more than two vertices, but V1 and V2 are vertices here. Picture. This is H, this is 2. You can find more or less n squared embeddings of H. One is squared such that they all induce the same edge length. And they all map V1, V2 to a pair, a distinct pair of points inside P prime. So each VI, V1, V2, embedded. And these pairs are distinct. I'm a bit lying here, but okay. But this is what we can prove. Right? So this almost gives a contradiction, almost improve this bound by a log n factor. But the problem is, so what is the problem? So the issue is that in this picture, we have, so H is rigid, we have all of these embeddings, they have the same edge length, so we expect them to be congruent to one another. So the red edges have the same edge length. But the problem is that these embeddings are not generic, so we cannot tell that for this specific embeddings, we get rigid frameworks. Okay? So this is the problem. Embeddings are highly non-generic. So H and PR not necessarily a rigid framework. Otherwise, we would be done in improving by log n factor.
One question, you think small graph H, small, I should think of small as fixed or one, or it's actually growing with?
No, so actually, if we could find a fixed one, then it would improve this even more substantially, but you should think of a log n.
But also, rigid doesn't mean two embeddings. Even in the rigid case, it only controls a neighborhood of an embedding.
That's true, but once you are rigid, then you have a constant number
I
of
see.
distinct.
And that the dependence of that constant is.
Yes, for example, here, this is rigid locally because everything, so it's like you should think of a algebraic map that takes the point, the embedding to the edge length. So everything is algebraic. You can bound the size of the pre-image if you know it is finite. Yeah, so here you have two distinct embeddings, but no more. So you do some pigeonholing. Okay. Good question. Okay, so this is not entirely the end of the story. So what do we need in order to complete the scheme? So I want to formulate it as a question in rigidity theory. So let me try to make the last step more clear. So how do we find this generically rigid graph H? In fact, we find a graph H. It has some more structure, but in particular, it has many edges. Whenever you have a graph with enough edges, more than a linear number of edges, you can always find a subgraph that is generically rigid in R2. But in our case, we get a graph, and we also get an embedding. And what we want a subgraph that when we restrict the embedding that we are given at the beginning, we will get a rigid framework. Let me show you the kind of statement that we need. So let's say we're given a graph with vertex and vertices and the edges, and let's say that we have many edges in some sense, n to the power 1 plus alpha. And we want to do, and we're also given an embedding. Embedding of this graph in R2. You want to be able to conclude that there is a subgraph H prime with at least 3 vertices such that if we restrict the given embedding to this subgraph, we will get a rigid framework such that H prime with same embedding, so P, restricted to the vertices of H prime, we want this thing to be rigid. Okay, so we start with a graph and an embedding, and we want a sub-framework. We want to find a sub-framework that is rigid. Okay? We cannot expect this to hold as I wrote it because there is this example of essentially the K33 example that I mentioned before. But no, I'm with the time. We can take a complete bipartite graph with this embedding, and for this embedding and K n over 2, there is no rigid subframework. The subframework will have this forbidden embedding. But if we add some additional weak non-genericity assumption here, so we can assume that additionally for every vertex, the neighbors of this vertex are not embedded to a common line. So neighbors H, not embedded to a line. If we add this assumption, then this is a theorem that we managed to prove, but for alpha, at least 1/2. So this is with Shorimoshi. Okay, so we have this as a theorem, but we need many edges. If you could prove the same theorem with a better parameter alpha, this would complete the scheme. So let me write a strong conjecture. I call it a strong conjecture because in this application we have more information about H. But let me just to be concrete. So strong conjecture. The theorem above statement of or alpha equals 1/6. Nothing special about 1/6. This is just what our analysis gives. So if this is true, then the structure theorem the strong conjecture implies small improvement in the unit distance bound, so x to the power 4/3 over log n. As I remarked before, if we will even I can make this stronger, maybe we can have a sub-framework that has constant size, then this will give a more substantial improvement here. So there is some room to opt for a stronger result. So this is what we know to show. Maybe last thing that I want to say is that this kind of statements, a statement that were not studied in the classical rigidity theory. So there usually people look at generic embedding. So this is a new kind of question also for rigidity theory people. And yeah, and we observe this connection to this problem of Erd H. So thank you for that.
I was wondering what kinds of like tools or techniques came into that proof.
Yeah, that's a good question. So actually it is related somewhat to this progress about the other problem of Erd H, the distinct distance problem, where Erd and Sharir managed to do some reduction of this problem to a question about incidences between lines and lines in R3. So what we do is we reduce this rigidity, this kind of rigidity problem to an incidence problem in R3. The basic property is that if you have P and Q in R2 and another pair P prime and Q prime in R2, you can associate with the pair P and P prime a line in R3, LP P prime, and with the pair Q and Q prime a line in R3. And these two lines intersect if and only if the distance here is the same. And using this property, you can kind of formulate this question in R3. Okay. And this is part of the Sharir work. This connection between the lines.
Then why these parameters show up, why this saves only log n, or why do you get a quadratic number of embeddings even though you would need much less?
Yeah, so actually there are many parameters, so I will not be able to answer everything, but the fact that the reason we get quadratic, this log n, not quadratic, the log n is because we use pigeonhole a lot. Because even if our framework, so first of all, we have many, where is the picture? With the, I erase it, okay. Where? Oh, yeah, okay. So you get many such graphs. You use pigeonhole in order to say that they are the same graph. Then you want to find a subgraph. I mean, you find a rigid subgraph, then use pigeonholing to say that it's the same subgraph. Then, because even if it is like it's already asked, even if you have rigid frameworks, they might have an exponential number of embeddings that are not concurrent. So you do another pigeonhole. So you really want, so the size of these graphs will affect how many, the pigeonholing. So if somehow you can find a constant size graph, then you're okay. But so this is why we lose here. Why exactly n squared? I'm not sure. I can show you more details, but I'm not. Yeah. There are many ways of the parameters. So you can get. So here, instead of in this conjecture, it doesn't have to be for 1/6. You can get another graph. It's like bipartite, very heavy on one, so you can get all kind of things, but I don't know why.
have I understood correctly? So this 1/6 is what you would need for the application, right? It's not like what you would expect actually to.
Right, so maybe it can be, so we know that you need more than n log n edges, but as far as we're concerned, it might be n to 1 plus epsilon. Yes, so we don't know. It's just for the application.
Okay, there are no more questions. Thanks.